All right, so we're talking about equilibrium reactions, and we have, if we have a given equilibrium reaction here, this reaction, we have some reactants, we have a product here. There is a double arrow to show us that these reactants come together to form this product. This product decomposes to form these reactants, right? And we don't know at equilibrium, is this reaction mostly reactants? Is this reaction mostly products? And we want to be able to have a value a number that will tell us right off the bat, is this mostly reactants or is this mostly products? And the way to do that is to write the number that the concentration of products over concentration of reactants would give us. And that value tells us about the relative concentration of reactants and products at the current condition. So which one of these would be an appropriate mass action expression here?
Let's see. Products on the top, so that's either A or C, right?
Well, products are on the top, yeah, that's for sure. But what about solid?
Oh yeah, you're not supposed to include solid, so that would have to be D then, right?
That's right. So D is the only one that has 1 on top, and that's the only product. So let's see, does that fit for our reactants?
Yeah, calcium ion to the third and phosphate ion to squared.
Okay, very good. So again, our mass action expression, and we could identify what the concentrations of these two reactants were, raise them to their values, 1 divided by that, and the product of this, 1 over the product of those values, that would be the current, the Q, the mass action value with a quotient Q that would tell us about the equilibrium of that reaction. Okay, so what is the mass action expression for the reverse reaction?
The reverse?
Yeah.
The reverse reaction. So we have, I don't know, what would we do?
Well, for the reverse reaction, this is now considered our reactant, and these are our products. So our products would go on top, so either A or B or C, and our reactant, which is this one, would go on the bottom. And because it's solid, it's not going to be included.
Oh, so it has to be B?
That's right. It's going to be B. Calcium to the third, phosphate squared, and then this is our reactant, and it is on the bottom, but is a solid, so it's not in the expression. Okay, good. So, under gaseous conditions, as we talked about when we were chapter 11, we were talking about gases can be expressed in terms of their volumes. They can also be expressed in terms of their pressures if we're talking about a fixed fixed volume for our reactions. So we can express a K, an equilibrium expression, in terms of concentration in molarity, or in terms of pressure. All right, now we're not going to we're not going to focus too much on this point here, but there is a difference between what we call Kc, where we're talking about K being in concentration, expressed in concentrations, and Kp, where K is being expressed in its pressures, the pressures of the gas, because concentration relates to pressure, right? We know that.
I forgot what K is.
K is the quotient when you are at equilibrium.
Okay, yeah. I'm not sure if that makes sense.
Well, I think it will as we move on. So just recognize that Q is the quotient at any given time, but K is where the quotient will adjust itself to once you reach equilibrium. Each chemical reaction, each equilibrium reaction has a different K value associated with it. And so that's when those values become valuable. The K value becomes valuable because that tells us already what the equilibrium will be once it's reached. All right. So, I don't want to focus on those problems there. These are just problems where we're relating Kp to Kc. We have an equation, and you can find this equation online anytime you want to, and just plug and chug. Okay, now, we just had a problem where we looked at the Q value, or the expression, Q expression, the quotient, moving for the reaction to left to right, and then for the reaction right to left, right? And we saw that to find that K, we essentially flipped it upside down. Another thing that we can think about is if I have this reaction here, A going to B, and I have well, let's use this example first for this one. If I have a K value, now this is an uppercase K now, right? So it's not a lowercase. You can tell the difference because this comes to the same height right there, right?
I know what an uppercase K is.
Yeah, but sometimes when we write it, we're in a hurry or we're just using our hands, we don't recognize the difference. Lowercase k was for the rate constant. Uppercase K is for our equilibrium constants. So if I have a K value here of 100, that means once equilibrium reaches 100, then the concentration of, when the concentration of B raised to 1 over the concentration of A raised to 1 equals 100, then we know that this reaction is at equilibrium. Okay? Well, what about this reaction here, where B is going to A? How would that, what would the K value for that reaction be?
That would be the concentration of A over the concentration of B.
That's right, products over reactants. Concentration of A over concentration of B. Now, what's the relationship between this value and that value? This equals 100. What is this going to equal?
It's just the inverse, right? A's on the top over here and bottom over there. Yeah, so it would be 1 over 100?
That's right, 1 over 100. So if you have a chemical reaction and you know it's K, again, that's the equilibrium or the quotient that will be reached once equilibrium is achieved. And then we have a different chemical reaction, we can know it's K simply by knowing the K for this reaction, and it will be the inverse, right? Because this is the expression for the K and for this reaction, and this is the expression of the K for that reaction. Well, what would the K value be for this reaction?
That would be products B squared over A squared.
That's right, products squared now over A squared. And how would that relate to this?
I'm not sure.
Well, let me pull this up a little bit, give us some more space. If you have B squared over A squared, that's equal to B over A squared. And if you don't believe me, you can put some numbers in there and go home and try it. It'll be a lot of fun. And therefore, B to the 1 over A to the 1 is equal to B over A. So how are these related?
Well, the one on the left is just the one on the right squared.
That's right. So I could identify the K value for this reaction as, if this one is K equals 100, this reaction 2A going to 2B in equilibrium is going to be that squared, or 1 with 4 zeros, 10,000. All right, so we reverse the reaction and try to find the equilibrium constant. It's going to be the inverse. We double the reaction and try to find the equilibrium constant. It's going to be that equilibrium constant squared. All right, one more scenario. Here's A in equilibrium with B. What was the K for this one?
That was 100.
Okay, we just made that number up for our, to simplify things for us. Here I have a chemical reaction, C going to D. Let's say this has a K of 13. All right. Would that information help me know the equilibrium expression, the equilibrium constant for this reaction?
I don't think they would be related, would they?
Well, the equilibrium expression for A to B, we said, would be the concentration of B over the concentration of A. The equilibrium for this one would be what? What would the expression be for here?
concentration of D over C.
Concentration of D over C. What would be this one here?
Concentration of products, B over, or times concentration of D,
Very good. Concentration of B times concentration of D.
over concentration of A times concentration of C.
Very good. Excellent. So then let's look and see how they relate to each other. So what's the relationship now between the equilibrium constant for, or equilibrium expression for this first reaction, the equilibrium expression for the second reaction, and the equilibrium expression for the reaction which is really the sum of these two reactions? So let me transfer them down here. B over A
Yeah,
and D over C.
yeah.
If I multiply these together, does that equal that one?
I guess so.
That's right. And so I can identify what the K would be for this reaction. It'll be the product, 1,300, the product of the Ks for these two reactions. Now the sum of these two reactions is this reaction, but the product of the two Ks is that reaction. All right?
Okay.